Dokie. We are starting at 1026 quiz 6. Did I call that right? Yeah, okay. Quiz 6 review. Going members only, weekly study sessions. Alright. We're going to start maybe a little after 4. I have to finish this little food and bring this food downstairs. Bring this dish downstairs. So, we'll start around 4:02 maybe. I'll be right back. Boogly. Alright. Alrighty. Well, I said we'd start at 4:02, but hey, it's 4:01. So, let's get started. You know what they say, under promise, over deliver. Alright. Welcome to the Math 1026 Quiz 6 review sesh. You all, or whoever's in 1026, have this quiz due this week. I think I have a fair amount of problems pulled up here to practice. We're going to be going over antiderivatives today. We're getting into antiderivatives and indefinite integrals, things like that. Okay, so let's get into it. Goodness gracious, sorry, I'm burping from this food. Alright. We're going to call this problem number 1. Let me go ahead and open this. And mute it. Alright. I think I just want to be able to see the chat here if need be. Alright. So, let's get into it. In this one, they say this function is an antiderivative of which of the following. So they're saying that this function is an antiderivative of which of the following. They're basically saying if we take the derivative of this given function, which of these functions in the answer choices could we get? And so going into these problems, I highly recommend reviewing derivative rules like quotient rule and product rule. These were ones you covered in 1025, and they are being used here. So we're going to start this problem by taking the derivative of this function. So as it's been the past however many weeks now doing these videos, all the problems I have pulled up today are ones that I have individual videos for. So there's there may or may not be any benefit in watching this video besides they're all in one place, and I'll kind of go through them relatively quickly. But in general, again, these weekly study sessions are meant to be places where you can send me problems and I can answer them during these sessions. So again, if you have any questions, you can always email me at carterdeeemath@gmail.com. So let's get into this. The first step is to take the derivative of this function. In order to do so, we need to use the quotient rule with this quotient here. I just want to address this minus 4 on the end. We'll have a derivative of 0, so that'll basically go away. We can basically neglect it. The derivative of e to the x cubed over 3x is what we're finding using quotient rule. So quotient rule is derivative of the top. So if we're calling this like a and b, numerator and denominator, we have a prime first. A prime would be 3x squared times e to the x cubed. that alone, that derivative a prime used chain rule. So I would recommend reviewing chain rule as well. A prime times b, so b is 3x, minus a, which is e to the x cubed, times b prime, which is just the derivative of 3x, which is 3, and all of this is divided by b squared. And so that is 3x all squared. All right, so here we're looking for some sort of answer that matches this. It's a little rough, but we'll see what we can do here. Okay, so they've gone about simplifying it in such a fun way here, so I'll try to make sense of how they simplified it. The first thing I'll do is combine anything I see here with itself and then anything I see here. So the left side there, we have a 3 times a 3, so that's 9. We have an x squared times an x, that's x cubed. We have an e to the x to the third. And then all of that is over 3x squared. So 3x squared is equivalent to 9x squared, because it's like 3x times 3x. And then we're going to subtract the other half, which is just 3, which is over here, times the e term. So 3e to the x cubed, and that is also over 9x squared. So basically I've taken this over this minus this over this. So I've broken up the whole fraction situation. Now we simplify each of these. So 9 divided by 9, 9's cancel. X cubed over x squared. We can get rid of 2 of the x's, so we're left with just a single x on top. X times the e term. And then 3 over 9 can reduce to 1/3. And that's probably the best we can do there. And that'll actually be answer D. We can see this term right here, maybe just written in a different order. And then we can see this term right here. And that's it. So not the nicest problem, not the kindest of problems, but again, it's still beneficial to review product rule, quotient rule, chain rule, and just practice a handful of these, try to get it down, at least enough to find the answer. All right, that was number 1. We'll go ahead and call this number 2, break it all down like so. Here's another example of the same problem. They give us this function. They say it's an antiderivative of which of the following, so we have to find the derivative of this function. Again, the plus 5 is just a constant, so its derivative would be 0, so we can ignore it. So here we're using the product rule to find the derivative of x squared times cosine of 10x. So product rule is a prime times b plus a times b prime. So a prime, the derivative of x squared, so let me back up. A is x squared and b is cosine of 10x. A prime is 2x, b is cosine of 10x. A is x squared, and b prime is the derivative of cosine of 10x. So a little bit of chain rule here. Derivative of cosine is negative sine of 10x, but then we need to multiply by the derivative of the inside layer, which is, so the inside layer is 10x, and its derivative is 10. So combining everything, we have negative 10 sine of 10x. And that's it. So this one, it's not as ugly in terms of like simplifying it. And so I think we can see 2x cosine of 10x, and then negative 10x squared sine of 10x right there. So C is our answer here. All right, good product rule example. That was number 2. Let's call this number 3. Which of the following is an antiderivative of this? Now, notice the difference in the language. This says this function is an antiderivative of which of the following. This one says which of the following is an antiderivative of this. So the annoying approach for these ones is you have to find the derivative of each of these functions and see which one equals ln of x. And so I'll demonstrate it with this first function. The derivative is the derivative of negative x is negative 1. Derivative of x times ln of x uses product rule. So derivative of the first, let me break it up here, sorry. This is A, this is B. So if we have A prime is 1, B is ln of x, A is x, and B prime is 1 over x. Now if we do the derivative of minus 5, that's again just plus 0, so we ignore that. If we simplify what we have here, we have a negative 1 plus 1 times ln of x is just ln of x times 1 over x. That's basically like x over x. So it's basically like we're adding 1. Negative 1 plus 1, 0. All we're left with is ln of x. So it turns out taking the derivative of the first function gives us ln of x, which matches the function they gave us. And so the idea is so since we took a derivative of a to get this, to get ln of x, then an antiderivative, a reverse derivative of ln of x is this, is option A. All right, I'm not going to go through the derivatives of the others. If you want to see those worked out, maybe watch my video I have on them. I might have done that in those videos. I have no idea. Practice derivatives. All right, which of the following, again, is an antiderivative of this? So the approach is still the same. We have to take derivatives. And so I can see the answer here only because I see the marking. Anyway, so I'm just going to show why the derivative of this is this. Okay? So derivative of this, we're using product rule. So I'll say first, we can ignore the plus 10. Plus 10 goes to 0. So we're using the product rule between A and B. So A prime comes first. A prime would be the same E term times negative 4. That in itself is a little bit of chain rule. So A prime comes first, B comes second, so this whole entire thing, plus A, which is e to the negative 4x, times B prime. Now the nice thing about B prime, the derivative of this, well, the minus 1 over 16 goes to 0, and then the derivative of just negative x over 4 is negative 1 over 4. Beautiful, right? So now the big goal is simplifying all of this. So let's demonstrate. We can start by distributing all of this, like this one term, to this and to this, because this and this are being multiplied together. So we can distribute to these two terms. Okay? So we have negative 4 e to the negative 4x times negative x over 4. So it'd be like times negative x over 4, right? Okay. And then minus, I'll just do it kind of the same way, minus 4 e to the negative 4x, and then times negative 1/16. How do I want to do that? Basically, a negative times this negative is going to be positive. Oh gosh, I'm sorry. I'm just going to stay consistent, and then I'll simplify it later. So I'll just do negative 1 over 16, something like that. Do negative 1, do it all over 16. I don't know. Making a mess of this, but you can see that I'm multiplying this by negative 1/16. Okay, that was that one. And then let's do this last one, just kind of blending these together. We'll go ahead and call this negative e to the negative 4x all over 4. So I went ahead and multiplied those two. Now, let's simplify some of the things we have here. We have 4 over 4. Those are gone. We have a negative times a negative to make this all positive. And I'll go ahead and throw this x in front. So we'll just say x e to the negative 4x. Yeah, all right. And then we have a negative times a negative. So here I'll go ahead and call this all positive. And then we have 4 over 16, which translates to 1 over 4. And now we can see that we have a positive e to the negative 4x over 4 minus e to the negative 4x over 4. So these cancel each other out, and we are just left with x times e to the negative 4 over x. So we see that the derivative of option C matches the function they gave us. Therefore, an antiderivative, like a single antiderivative of the function given, is option C. I know these are a bear They're not very fun, but again, just practice derivatives. Do the best you can. No one's going to hate you if you can't simplify these. These are very challenging. These are tricky to simplify. Okay? If you have any questions, just let me know. All right, that was number 4. We'll call this number 5. All right. So, given this function, an antiderivative of f is what? So if you wanted to, you could take that same approach, like take the derivative of this, or you could start thinking in reverse now. So here we start getting into the actual methods of finding antiderivatives of functions, rather than having to take the derivative of all these and see which one matches that. So if we think about it like this, if 1 over x, I guess if we're finding the antiderivative of 1 over x, we want to think about what's a function whose derivative is 1 over x. Is there any function we've dealt with in the past that has a derivative of 1 over x? Yes, that function is ln of x. And it's kind of just like a pattern or a formality situation, but anytime you take an antiderivative of 1 over x, it's important to not only call it ln of x, but include the absolute value bars around the x. It has something to do with, I don't know, keeping everything positive on the inside, something like that, because you can't have natural logs of negative numbers, something like that. All right, we'll keep that rolling. Let's keep this rolling. That was number 5. This is number 6. So in number 6 here, they give us this function, 1 over t to the 11th power. Here, we are going to demonstrate, kind of like when we were taking derivatives of functions like this, where the variable starts in the denominator, we want to first rewrite this function. We want to rewrite it so that it's t to the a, or x to the a. We want to rewrite it so that it's in the form of a power function. So in doing so here, this 1 over t to the 11th could be rewritten as t to the negative 11th. In doing that, we have now a power function, so we're going to find its antiderivative, often notated with a capital F of t, and what we're going to do is something known as the reverse power rule. So there's the power rule when taking the derivative, which was like bringing out the value and subtracting 1 from the exponent, but here's the reverse power rule. We're going to add 1 to the exponent, so the previous exponent was negative 11, so we're going to add 1 to that to get negative 10. Whatever this new exponent is, we are going to now divide by that value. And we're done, essentially. It might help to rewrite any terms with negative exponents so that they do not have negative exponents anymore. So what I mean is we can bring that t to the 10th to the denominator. Obviously, I've made its exponent positive because bringing it from the numerator to denominator makes that happen. And the negative, we can probably just bring out in front or put it up top. But something like this is what we're looking for. Negative 1 over 10 t to the 10th. That is option B. That was a little demonstration in reverse power rule. So we add 1 to the exponent and divide by whatever that new exponent is. That was number 6. Here's number 7. This function 7, they're asking what is the indefinite integral of 7 dt. Now all this means is we're finding the antiderivative of 7. When we think about it like this, we're finding the antiderivative of 7. So the question is, what function would have had a derivative of 7? Well, we learned back last year, whenever you learn derivatives, that anytime you have a constant times x or a constant times t, the derivative of a constant times t is just the constant. So, working backwards, if we're just given the constant, then the antiderivative will be the constant times t. And it's important when you're taking indefinite integrals, this little squiggly sign here, to add plus c, because plus c represents some constant that could have been there. And basically, if you just said 7t, you wouldn't be like entirely wrong, but like adding plus c makes it so there's a whose family of functions whose derivatives would equal 7. So it's kind of a formality thing, but anytime you see the squiggly line, the integral sign, you must take the antiderivative and add c to it. So 7t plus c is what we're looking for here. That was number 7. Let's go ahead and do number 8. Number 8, we're given this function x to the 10th. They ask, what is the integral of that function? So what's the integral, the indefinite integral of x to the 10th? When I say indefinite, I'm basically saying there are no boundaries. We're not integrating from one x value to another. So indefinite, that's the definition. To take the indefinite integral is to find the antiderivative. So here we can practice our reverse power rule, where we're going to, since it's already in the form of x to the a, it's already in the form of a power function, we can add 1 to the exponent to get x to the 11th and divide by whatever the new exponent is. So x to the 11th over 11, oh say can you see, and we get option B. That's it. A little reverse power rule. Hope that makes sense. It's not too crazy. Let's do number 9. Number 9, we have this function e to the t, and they ask what is the antiderivative or the indefinite integral of e to the t. Now, e to the t was special, right? We knew back when we learned the derivative for e to the t that its derivative was just e to the t. So, if you're finding the antiderivative of e to the t, it should be no surprise that it's e to the t plus c. Don't forget to add plus c. You gotta see it. All right. So D is our answer here. We're cruising through these. We only have a few more, to be honest. It might be like a 30-minute session. That was number 9. Here's number 10. They give us this function, sine of t, and they ask for the antiderivative or the indefinite integral of sine of t, dt. It might help to recall the derivatives of sine and cosine. I'll give you a little visual, mnemonic kind of device, sort of a visual device. I don't know. A little memorization trick. When finding derivatives of sine and cosine and so on, you can use this kind of cyclic nature, this cycle of derivatives, because they always cycle back. The derivative of sine is cosine, the derivative of cosine is negative sine, and so on all the way around that little oval there, little circle. Likewise, if you're finding antiderivatives, the cycle works as well, just backwards in the opposite direction, right? So the antiderivative of cosine is sine. Antiderivative of sine is cosine. Antiderivative of negative cosine is negative sine. Antiderivative of negative sine is cosine. So these are all the antis. And so in this case, if we're following the anti-path, the anti of sine of t going in the blue direction would take us to negative cosine. So negative cosine of t. And oh say can you see? So B is our answer here. Alright, that was number 10. Here's number 11. I think I have 3 examples of this, and then we might be done. Alright, let's jump right into it. Number 1, e to the t has exactly one antiderivative. So we know that the antiderivative of e to the t is e to the t. But to say it has exactly one is not exactly right, because what are we forgetting? Oh, say can you see, right? So an antiderivative, finding an antiderivative of a function is really, like, you can think about it as finding just like one antiderivative for the most part, but like it's sometimes important to think about antiderivatives as like a family of antiderivatives. So as a family, what I mean is like you're finding like a general antiderivative of a function each time. And so when we have plus c, that c could be any constant realistically. So it could be like, you know, we could have e to the t plus 1, e to the t plus 10, or e to the t plus 100. You get the idea. And in this family of functions, all of these have the derivative e to the t. And so to say that the function e to the t has only one or exactly one antiderivative is false, because all of these are antiderivatives. These are just a few examples of antiderivatives of e to the t, right? So that's why we add plus c, and to say it has exactly one is false. All right. Given this indefinite integral, we have 2x plus 5, and they tell us the integral, or the antiderivative, is x squared plus 5x plus c. So you could check this one of two ways. You could do reverse power rule with 2x plus 5, or you could do power rule with x squared plus 5x plus c. You could take the derivative and see if it matches what's inside here. So I'm going to practice antiderivative. So the integral of 2x plus 5 dx. So the integral of 2x, you could do our reverse power rule, where we add 1 to the exponent and divide by that new exponent, and then 2 over 2 cancel, so you're left with just x squared. And then if you have just a constant, the antiderivative of just a constant is the constant times x. And then if you're taking the antiderivative, or the indefinite integral, you got to add c plus c. So x squared plus 5x plus c checks out. So 2 is true. Number 3, the indefinite integral of f with respect to t represents all possible antiderivatives of f of t. That sounds pretty good. Yeah, that's exactly right. So the indefinite integral, for example, like what we just found, the indefinite integral with the squiggly and the dx, the indefinite integral with respect to t represents all possible antiderivatives. Now, key phrase is all possible. All possible antiderivatives is, kind of a result of adding plus c. We always find all possible antiderivatives by adding plus c. Plus c makes it so it's like a family of possible antiderivatives. It's a general solution, general antiderivative. I don't know. So in this case, 2 and 3 are correct, and 1 is our false statement. That was number 11. We'll do, I think, 2 more of these. Here's number 12. Let's get into it. Number 1. Whoa. The indefinite integral of f with respect to t represents exactly one antiderivative of f of t. False. That's kind of the opposite of the statement we just had, right? They said represents all possible antiderivatives, and that was a true statement. So to say the indefinite integral only represents one is false. Number 2, the indefinite integral of f with respect to t is the integral of f of t dt. Checks out to me. Yeah, it's kind of just throwing it in the integral sign with the dt. It looks good. Yeah, I think that's right. Number 3, the indefinite integral of e to the negative x is equal to negative e to the x. Great question. Well, let's start with this. Let's say we were taking the derivative of e to the negative x. The derivative of e to the negative x would be first e to the negative x. The most important thing with any exponential function, whether you're taking the derivative or antiderivative, is that the exponent's going to stay the same. You should see the same exact e to the negative x across derivative or antiderivative. It does not matter. Now, with the derivative, you would also do chain rule, so you'd like pull out a -1, which comes from the derivative of negative x. So -1 e to the negative x. And in fact, in this case, that should also be the antiderivative of e to the negative x, but for a particular reason. I'll tell you why. Let me erase this. The antiderivative of e to the negative x, we'd start with repeating the same e term, e to the negative x. Sorry, my stuff just froze there. E to the negative x, and we would then divide by whatever the coefficient is to the x term. That's kind of a trick with e functions. So e to the negative x, we repeat the same e term, and then we divide by whatever the exponent is. For example, had it been e to the negative 3x, the antiderivative would be the same exact function, e to the negative 3x, but then we divide by -3. Okay? And of course, we'd add plus c on both those. So this was just a random example here, right? Just to show that rule. So what am I proving? This is equal to negative e to the negative x plus c. Negative e to the negative x plus c is close to what they have here, but they're missing the negative in the exponent place. So this is false. Looks like only 2 is correct here. Nice. That was number 12, and we just have one more, I believe. Call this number 13. We'll be on our way. Starting with number 1. The indefinite integral of f of t equals f of t plus c if capital F of t equals f prime of t. Now, what the heck does this mean? Let's start with this first little unit here. The indefinite integral of lowercase f of t dt equals capital F of t. So this is saying capital F of t is the antiderivative of f of t. If capital F of t is the antiderivative of f of t, then that means if we took the derivative of capital F of t, if we took the derivative of this, we should get what's on the inside every time. So I just wrote this. Does what I wrote match what they wrote? No. So, false statement. That's it. Number 2. The indefinite integral of 3z squared equals z cubed. So, again, you could take the antiderivative of this, see if it matches this, or you could take the derivative of this and see if it matches that. Now, I guess the problem with that is, hopefully you notice something about this right side here. If you don't, we'll address in just a sec. So let's do the reverse power rule. We're going to practice taking the antiderivative. Antiderivative of 3z squared. We add 1 to the exponent to get 3, and we divide by that new exponent of 3. 3's cancel, and we're left with z to the third. Oh, say, can you see? All right. What are they missing? They're missing C. All right. That whole thing, or missing C, makes the whole thing false. False. Got a lot of stuff jammed up here. Hold up. Okay. Number 3. T cubed minus 6 is an antiderivative for 3t squared. Very interesting. Pretty much the same question as number 2, but let's talk about it. An antiderivative for 3t squared, we basically just said that the indefinite integral for 3t squared is t cubed plus c. Again, plus c creates a whole family, as I keep calling them, family, a general antiderivative for 3t squared, right? So t cubed plus c is basically all the possible antiderivatives. And so to say t cubed minus 6 is the same as a plus c, where c is negative 6. And so t cubed minus 6 is definitely an antiderivative for 3t squared. You could also just think about, like, if you have t cubed minus 6 and you took its derivative, you'd get 3t squared plus 0, or just 3t squared. And yeah, that would also prove this one true. So only 3 is correct here. Hope that makes sense. This was just a brief insight into antiderivatives and a big hint to go ahead and review your derivatives, your product rules, your product rules, your quotient rule, your your chain rule. A lot of antiderivatives, so it's on my mind, I guess. I'll just do a quick scroll through of the problems we worked out today, and we'll go ahead and call it. Again, if you have any questions, you can always send them my way. I'm not I'm not afraid to answer any questions. Hope you're not afraid to send anything. Always happy to help. All right. Thank you so much for watching, whoever's watching out there. And I hope everyone had a wonderful spring break. Hope you're excited to get back into math stuff, get back into the semester, and go and knock out this semester. Because, yeah, it'll be cool to knock out this semester. I don't know where I was going with that. It's good to be back. I don't fucking know. All right. Have a great one. I'll see you next week on Quiz 7. Send me questions. Yeah.